for having in the first place invited me to give this course of lectures and then making all the arrangements to suit my convenience. Apart from Simon, I would like to thank Romesh Kaul, because it was Simon and Kaul who first suggested that I should give this series. That was in March or some such time. And then Bhaskaran, Rajashekharan have always been supporting me, not to speak of V. Srinivasan. So I really take this as a challenging opportunity to talk on this subject. I have not done so for a long time now. So I would like to say that I have rather ambitious aims in this course. I want to cover a fair amount of material, and I hope you will find it useful and interesting, and I hope that many of you will continue to attend these lectures. About the style of the lectures, well, first about the title. When I was asked for the title, I was reminded of a famous set of lectures given by Wolfgang Pauli in CERN. I think it was in 1954, and I think the title was Continuous Groups in Physics or some such thing. And it was those lectures are printed in the Springer series, the green book. I don't remember the name of Wissenschaften Physik or something. So I borrowed the title of these lectures from those Pauli lectures. In retrospect, if you go and read Pauli's lectures, they are quite brief and the amount of material covered is quite limited. As I said, I have tried to be rather ambitious and to cover a fair amount of material. So the aim of this course is to present some of the theory and useful facts about groups and their representations in a way which I think is appropriate for a physics audience. I will not be giving proofs of all the statements that I will make. My aim is to be really descriptive, describe concepts, describe relationships between concepts, describe results, and in due course I will give a series of references, a list of references, and those of you who are really interested should see how some of the results which I describe can actually be proved. But I repeat, I will not myself prove everything that I say. Initially, we will discuss the theory of finite groups and their representations. This I will do so that the basic ideas and the basic results become familiar to you. And later, when talking about specific groups, then I will turn to continuous groups. And among them, I will be dealing in fair amount of detail with the so-called compact simple Lie groups and Lie algebras and their representations. And towards the later part of this course, I will talk about continuous groups which are related to transformations on space-time, both non-relativistic and relativistic, and the corresponding representation theory, and so on. So you can say that the spirit behind these lectures is to provide you with a user's manual for group theory, especially continuous groups, as they arise in physical problems. The things that I will assume are basic set theory, theory of linear vector spaces, transformations on vector spaces, linear operators, how matrices arise, vector spaces carrying an inner product, and so on. So all of this I will assume you all know. In fact, many of the things I am going to describe may also be known to some of you. Let me hope that there will be something new for each one of you. I think the full set of topics is 8 in number, 8 major topics, and they are available. They might even be circulated. They have been shown to you. So this is by way of introduction, and now let me get started. So I will begin with the definition of a group. It is not necessary to say that purpose here is not to attempt to be rigorous, but just make sure that the basic ideas are clearly understood. Right? So what is a group G? The other thing is, please feel free to interrupt me and ask any questions, and when possible I will answer them. So what is the definition of a group? A group is a set of, it's a mathematical object. It is a set of elements for which we will use symbols like A, B, C, H, G and so on, with certain mathematical operations or properties given. What are the mathematical operations? The most important is what is called the composition law, or it is sometimes also called multiplication law, group multiplication law. So what is this procedure? It is a procedure which I will describe, and it must obey certain conditions. Do you wish to keep some? Okay. Is this writing visible? Is it bright enough? Okay. So what is this group composition law? It says, given any two elements of this set, say A and B, a third element which is written as AB for the moment is determined, and it is called the unique product of the elements A and B, and so this product also belongs to the group. So this is the composition law or the multiplication law. Sometimes people call it a binary composition law, because you have to start with two elements and then the group tells you what is their product. Now what are the properties which this composition law must obey? First property is associativity. Take any three elements in the group, you can easily see that there are two ways in which you can determine their product. You might multiply B, compose B and C first, and given the result compose it with A, or you might compose A and B first and then compose with C on the right. The associative law is a requirement that this must always be the same. It should not matter in which sequence you use the composition law for two elements at a time, and since it should be the same in either way, we just write it as the product ABC without any brackets anywhere. Of course, the sequence in which the three elements are written is important. So this is the associativity. The next condition is that there should be a special element in this set, in this group, which is called the unique or the identity element, and it is that for which I have used this symbol small e. It must have a special property. If you compose any element with the identity, either on the left or on the right, the result must be that element. It must be unchanged. So for all group elements, multiplication on left or right by the identity should not change the element. And the last one is the existence of inverses, which are also unique. For any element of the group, there is a unique element called its inverse, with the property that composition of an element with its inverse in either order should always give back the identity. Now I have written down all the laws that must be satisfied in order to have a group. It is possible to re-express them maybe in a slightly more economical fashion, so that you distill the essential set of requirements, but I will leave it in this form and just make sure that you grasp all these properties. All right. So, a group is a set of elements with a composition or multiplication law which has properties of associativity, unique identity, and for each element a unique inverse. Now, if you look for examples of groups, you can easily imagine several qualitatively different possibilities. First possibility you can think of may be a group G with a finite number of elements. In that case, we say the order of the group is the number of elements in the group, and it is often written as G within square brackets. So, that is the notation for a group with a finite number of elements, and as I said, for the general representation theory we will always keep in mind this kind of group, though in later practical applications we will go to the infinite case.
Why is it called multiplication law?
It is just a name. If you prefer the word composition, it is better in some ways, but it is just called group multiplication. The word multiplication can lead to some misunderstanding because law, rule, something which you should obey. All right. Multiplication rule, if you like. Not a property, it is a prescription. Given two elements, how do you determine a third one? So, you can, if you wish, you can call it a rule, but not property is not a very good word in this context. These are the properties of this law. All right. So, these are legitimately to be called properties. Properties of what? Of this multiplication rule or this multiplication law. So, there is a slight difference in status among 1, 2, 3 and 4. 2, 3 and 4 are conditions which must be obeyed by 1. Okay. So, one possibility is that you might have a group of finite order, finite number of elements. Another possibility, let me just list them, is that you might have a group with an infinite number of elements, but they may be discrete. That is, you can number them, you can talk of the first element, the second element, the third, and so on. We will see examples of each of these in a little while. Another kind of infinite group can be imagined, an infinite and continuous group, in which case G is a manifold of some dimension. And in fact, the most part of this course will deal with infinite continuous groups, and at this moment I just mention it as one of the possible things you can easily imagine. So, let us look at some very standard examples of groups. The first would be an example, standard example of the finite groups, and that is the group of permutations of n symbols. Now, I will certainly not go into much of the representation theory or the structure of the permutation groups in any detail, but I will just introduce the symbols, the notation, so that you can at least on your own make sure that all the conditions for a group are obeyed. So, what does the permutation group on n objects or n symbols look like? Well, first, it is indeed true that it is a finite group. And what is the order of this group? How many elements does it have? As you probably all know, it has n factorial elements. Now, there are many ways in which an element of the permutation group can be written. All of them are useful, and you must learn, if you deal with the permutation group, to deal with all of these notations. A permutation P, the first way you can think of writing or describing a permutation is to do it in the following way. You list the numbers 1, 2 up to n as the top row in this symbol, and below each one you write the number into which P carries the number above. P sub 1 is one of the numbers 1, 2 up to n. It is the image of 1 under the permutation P. P sub 2 is the image of 2 under the permutation P, and so on. So what are the numbers P1, P2 up to Pn? They are the same as the numbers 1, 2 up to n written in some other order. So of course, there are no repetitions among these numbers. Every one of the numbers 1 to n appears there in some other order, and therefore you see immediately the number of permutations is exactly n factorial. Sometimes it is convenient to compress this symbol and write it as j above and the image P of j below, with the understanding j runs over the range 1 up to n. You can also easily appreciate there's a lot of freedom in writing a permutation in this way. You may interchange the first and the second columns, no change in the permutation. You may interchange any number of columns, always keeping 2 above, P of 2 below, 4 above, P of 4 below. Don't destroy any column, but rearrange them in any way you like. You are still describing the same permutation. Here's one more way in which a permutation can be written. Let me just show you. You start with the number 1, the first element in the set of n integers. Then you write the image of 1 under the permutation P. Then you write the image of 1 under P. And go on doing this as long as you keep getting distinct numbers. At some stage, you might reach some integer between 1 and n such that P of that brings you back to 1. Then you stop. Then you say, let's suppose that this does not exhaust all the integers 1 to n. So take something which is not contained in the first bracket. Let us call it j. Then you write P of j, then P of j, and so on until it comes to a close, and so on. Then you start a third bracket if necessary with some k, which is not any one of the first set of numbers, not any of the second set, and then apply p to k, p squared to k, and so on. So this is a way of also writing a general permutation. It is called the cycle representation of P. So maybe I should complete this. And there may be more factors. So what you see is that these are so-called disjoint factors or disjoint cycles. The numbers which appear in the first bracket, none of them will be repeated anywhere else. Those in the second will not be repeated anywhere else, and so on. So that is why these are disjoint. So any permutation can also be written in this manner as a sequence of disjoint factors. And there may be other ways also. Now what is a composition law? to make sure that you do have a group. Here these various notations become handy. So let us start by depicting the two permutations Q and P in that fashion. I am using this compressed notation. So in the first factor, K is understood to run from 1 up to n, and in the second factor, J is understood to run from 1 up to n. Now what I will do, in order to arrive at the result of composing Q and P, I will use the fact that for the permutation Q, I can reorder the columns in any way I like. It will not change Q. So what I will do is take the upper entry to be P of J, the result of applying the permutation P to J. What should I write in this position to make sure I am describing the same permutation Q as before? I would like one of you to tell me what should be written here, just to make sure that you are comfortable with the notation. Huh? Q of P of J. Very good. Q of P of J. This way of writing it allows us immediately to state that the composition law is the following. You imagine the permutation P applied to J, it has as image P of J. To this you apply Q, and you get the image of P of J under the permutation Q. So this defines what we mean by composing or multiplying two permutations. If you like, this is the definition of the group composition law for the permutation group. And now it is an exercise for those of you who have not done this up to now. It is an important exercise to convince yourself that this definition of composition for these symbols has the associativity property. I would like to urge you, if you have not done it ever earlier, to please go through the algebra, make sure you understand why the associativity is satisfied. Let me ask some other questions in this same context. Again, some of you may know, some of you may not. What is the representation in this manner of the identity element in this way of describing permutations? What should I write for E? First I will put 1 to n. What do I put in the lower part? Same thing, no change. So this is the identity element. You must now verify that this identity element functions as we desire in this way, AE equals EA equal to A for any A or P or Q. You must make sure, using this composition law, that this is the correct choice of permutation for the identity. What would be the way in which we write the identity if I use this so-called cycle notation? If I want to write the identity element in this fashion, can any one of you tell me what it would be? 1 in a bracket or by itself, and then by itself, and so on. Correct. So it means that the unit element is a product of n factors, each one containing only one number, 1, 2, 3, and so on. what would be the inverse of the element P if I use this notation for describing P? What would be its inverse? What should I put on top? What should I put at the bottom? Pj at the top, J at the bottom. Again, you must verify. It's not very complicated, but you must do it if you have not done it before, that this is a satisfactory definition of the inverse of a permutation. There is a unique inverse for every P, and it has the property which we have demanded. So, as I said, all the laws of group structure should be checked, and I will leave that as a simple exercise for you. So, this is standard canonical representation, description, a standard example of a finite group, the permutation group on n symbols. So, that is it, order n factorial. The theory of this group is extremely rich, and so many mathematicians have spent so much effort in studying this group and its representations. This is a word which I am introducing now, which we will study in greater detail. The meaning of representation we will study in great detail as we go along. This is being videographed, right? This lecture. Jokes are also allowed. They are allowed.
In fact, possibly more jokes.
Yeah. So I am reminded. See, a great part of the theory of the permutation groups and its representations are associated with the name of an English mathematician by name Alfred Young. Young's name appears all over the place in the theory of this group and its representations. And I learnt from my teacher many years ago that Young lived and worked about a century ago, and he wrote one or two important papers around 1908 or 1909, something like that, say a century ago. Maybe the first paper, the second, something like that. And then for 20 or 25 years, there was no more paper. And then sometime in the 1920s, sometime late 1920s, he wrote the next paper in that sequence. And this is apocryphal. This paper in the late 1920s starts with the words, "As we showed in our previous paper." This is just to show it is a very interesting group. It is a very demanding group. And I have heard from friends that the study of the properties of the permutation group and its representations is a triumph of algebraic technique. One of our friends, Professor Subhash Chaturvedi, is very familiar with these groups and with the literature related to it. Many statements and theorems about the permutation group, they are very difficult to describe to another person. You have to just absorb it internally. Partly this is because it is not a continuous object. There is very little, almost no room, no place for calculus, for differential ideas, for things of that nature, which is what most of us physicists are more familiar with. But you know it is important for physical purposes also. Okay. The next, so this I wanted to spend a little bit of time just to introduce you to different notations for permutations and so on. So this was the first example of a group. It's a finite group. The other examples I will be rather brief. suppose you consider all integers positive, negative and 0 with respect to addition as the group composition law. So this example is intended to show you the use of the word multiplication to describe the law of combination of two group elements can be sometimes misleading. Addition is a group multiplication law. But you are sophisticated enough not to be misled by such things. When you use the word multiplication in the context of a group operation, you realize it's a group operation. It's not ordinary multiplication. So if you consider all integers positive, negative and 0 and take the group composition to be addition of integers, this is indeed a group. And what is the integer that plays the role of the identity? It is the number 0. What is the inverse of any integer in this context? Please tell me. It is not 1 by that number, it is a negative. So all these words have multiple meanings and we always have to remember the context. So what kind of group is this? I had given some examples of different kinds you can imagine. Is it a finite group? Infinite and discrete. Good. Here is a third example. All positive, real, or if you wish, you can also restrict yourself to rational numbers with respect to multiplication. Now this means multiplication in the familiar sense, the product of two real numbers being another real number. So here you can immediately see the identity is the number 1. The inverse is the usual inverse. And you can immediately see by usual inverse, maybe it is better I write reciprocal. You can see this is also a group. You can immediately see that all the laws are obeyed. What kind of group is this in terms of that classification? If I consider all positive real numbers, what kind of group will I get? Infinite continuous. But if I limit myself to all positive rational numbers, what kind of group will I get?
Discrete.
Infinite discrete. Because rational numbers can be counted one after the other. Fourth example. Any linear vector space with respect to addition of vectors. In this case, the identity is the 0 vector and the inverse again is the negative of a vector. For our purposes for physical applications, we will only be concerned with real or complex linear vector spaces, nothing more complicated than that. Few more examples so that you get into the spirit of things. Now we move towards continuous groups, and I list a few. The groups, these are also groups. I am giving you examples of groups. What is SO2? It is a set of all proper rotations in a plane. We will describe this in a great detail in the later section, section 2 of this course. So I will not write everything now. So SO2 is the set of all proper rotations, we can say right-handed rotations in a plane, it is indeed a group. O2 is a set of all orthogonal transformations in the plane in which you allow proper rotations as well as improper rotations, that is where one of the two axes, let us say out of x and y, one is taken to its negative, the other is left alone. That would be a mirror reflection. SO3 is a group of all proper rotations in physical three-dimensional Euclidean space. So it's a group of orthogonal transformations in three real dimensions which preserve the right-handedness of a coordinate system. That is a group. O3 enlarges proper rotations to allow for space reflections, and so it is called the orthogonal group in the full orthogonal group in three dimensions. So as I said, the second section of this course of lectures will look at these groups, their definitions, their properties, their composition rules, etc. in considerable detail, partly because these are the most important groups for a large variety of physical problems. Also, our description of these cases will prepare the language, will prepare the ground for more detailed and extensive study later of all compact Lie groups. So what kinds of groups are these? They are infinite and continuous. Not totally continuous in the sense you can see intuitively, if I write S, it means special, it means no improper rotations. So this is a continuous, a connected continuous manifold. This group of proper as well as improper rotations in the plane or in three dimensions, it is continuous, but it is not a connected thing. This is made up of two parts, this is made up of two parts, each of which is connected within itself. Well, we will describe all these properties more carefully later on. You can also consider, well, I am going to introduce this word subgroup right away, though I will define it formally later. There are subsets of rotations in a plane or subsets of rotations in three dimensions which will preserve any given regular figure. For example, an equilateral triangle or a square, or in three dimensions a cube or a regular tetrahedron, and so on. So those rotations in three dimensions which preserve a given regular geometrical figure, they will also form a group. They will be a finite group. They are pulled out of the group SO3 and so on. These real rotation groups can be generalized in two very
I'd like to add that
Yeah.
this is what they call point groups.
point groups. Yeah, they are called point groups, and if you allow discrete translations, then what are they called? Space groups. So point groups are groups with finite numbers of elements. Space groups are infinite discrete groups. Okay. Now this idea of rotation in two-dimensional plane or in three-dimensional real space can be generalized in two independent directions. The one is to make it applicable to any number of real dimensions, and then you deal with groups called the proper group of proper rotations in n-dimensional real Euclidean space, that is called SON. We are going to study SON in great detail sometime later. The second direction in which you can generalize this concept of a rotation is to go from a real vector space, a Euclidean type vector space, to a complex vector space with a Hermitian scalar product, and then one arrives at the very important family of continuous groups called the unitary family. So here I have given you so many examples to show you how different cases can arise. The last example I will list here, the last case, is groups which are related to space-time. Space-time related groups. So these, I just give you the names, and I do intend to discuss these towards the end of the course. The Euclidean group, the Galilei group, which is basic for, I'm sorry, my handwriting is degenerating. I think I should not write so low down on the board. The Lorentz group, which is important for special relativity, the Poincaré group, and so on. So all of these, which we will study towards the end of this course, are groups related to the properties of space and time, and they are continuous infinite groups. Now, one elementary definition, and then a way of describing the elements of a finite group. The elementary definition is the following. Suppose you are given a group G. So, G is given. If the result of composing A with B is always equal to the result of composing B with A, for all A and B, if this is true, then it is called an abelian group. However, if at least some cases AB is not equal to BA, then it is called a non-abelian group. So the abelian means commutative. Non-abelian means non-commutative in general. That means in the non-abelian case, it is not that always AB differs from BA. It is just that there are at least a few, one or more pairs of elements A and B, for which the product depends on the order. Okay. Now, you can go back to all these examples and easily see which ones are abelian, which ones are not abelian. Permutation group, Sn, is it abelian or not abelian? Anybody can tell me the answer? Huh? Not? For what n? S2 is abelian. S2 consists of only two elements, one transposition. Pardon? So n greater than or equal to 3, permutation group is not abelian. What about example 2? Abelian. 3, 4, abelian. 5, this is abelian. As I said, we will describe this in great detail later, but it's quite interesting. Rotations in a plane, proper rotations in a plane, this is abelian. What about O2? Rotations and reflections in a plane? Yes, abelian or not? If you don't know, it won't be easy to guess. You have to do a little bit of work. We will see. It's very interesting. Such a simple problem, it is not abelian. SO3, rotations in 3 dimensions, not abelian right from the start. And therefore also, all rotations, all improper and proper in 3 dimensions, also not abelian. These fellows, for n greater than 2 in this case, n equal to 2 and above in this case, they are also not abelian. And all the important space-time symmetry groups are all non-abelian. Structure of a finite group can be very nicely, before that, there is a very important property which can be called the cancellation law, which is always available when you have a group in your hands. Suppose you have 3 elements in a group, A, B, and C, and you are told that AB equals AC. Can you draw a useful conclusion from this? This implies and is implied by B equal to C. You know why this is true, how it is easily proved. What do you have to do? And then everything falls through. And in the same fashion, it could have been the other side also. So these are called cancellation rules. Huh? What do you mean by A is 0? Huh? Yeah. No, so you look at one of the examples that I gave earlier. Which one? The integers. Right? Take the case of all integers, positive, negative, and 0. Under what operation did it form a group? Can you look at your notes and tell me? It is with respect to I think it is example number 2, the way I wrote it. That was a case where the number 0 happens to be an element of the set, but what was the group operation? Huh? Addition. So you have to be careful. All right. Now there is a simple concept which people use in teaching this group theory in the beginning for the new students. It is called the idea of the multiplication table of a group. Well, I think from the video point of view, this is very bad. Anyway, I just want to describe what is the concept of the multiplication table. The idea is that you make up a table in which on the top row you list the various elements of the group. This is for a finite group to be doable in a finite amount of writing paper. List all the elements of the group on top, start with the identity. And in this column also, list all the elements of the group starting again with identity. So I use the symbol A for a general element of the group in this column and B for another independent general element in that row. And then you fill in this table, you write at each intersection the result of the composition of the A with the B. So what will I write here in this first position? E. And go on like that. What will appear here? No change at all. Here it will be A and so on. What shall I write here? I write AB. So this is just a definition of how this table is to be constructed. The group element which you will write in this position in this table is the result of the product A on the left, B on the right, just an agreement to construct the table. So if you want to get practice, if some of you are new to group theory, well, start with the simplest case of permutation on 2 objects. It has only 2 elements. Draw up the multiplication table. Then, and that will be extremely simple. Then you do a similar exercise for the set of permutation on 3 objects. How many elements? 6. So you will have to write out a table like this with 6 labels in the column, 6 labels in the row, and therefore all in all 36 entries. And if you are new to the subject, you must do this to get familiar with these ideas. And please appreciate when you do this, the entries that appear here must be consistent with all the conditions for a group structure. All the group laws must be obeyed by the entries which you put here. In other words, you can't say, I will define a group, I will invent a group by writing some arbitrary entries all over here. You must make sure that what you write in this table obeys the associative condition, inverses, and the properties of identity. That, of course, is already ensured by this row and this column. But you must make sure that all the other laws are consistently obeyed. For example, in any given row in this multiplication table, what will the entries be in any given row? Well, in the A th row, it will be A times E, A times the next element, A times the next element, A times B, and so on. Convince yourself from these cancellation rules. In every row, all the elements of the group must appear. None of them can be missing, and each one must appear exactly once. Convince yourself if it is not clear. The same thing is true for every column. Every column contains all the elements of group, each one once, but in some other order. All right, and this is called the idea of the multiplication table of a group. And for sufficiently small numbers of elements, you can do this with a finite amount of paper. These days, even large size computer sheets are not available. When a few years ago, we had good supply of those things, but not anymore. Huh?
So when you say every row will, every element will appear in every row. Saying that every group is essentially a subgroup of the permutation.
Yes, correct. So I hesitated to say it because formally I have not defined subgroup, but you can now see from what Simon has said, each element of the group can be made to correspond to some permutation of n elements. Okay, and it will be a subgroup as we will formally define in a little while. So now I want, so these have been definitions, examples, and the multiplication table. Now I want to deal with a series of operations which are meaningful, and of course I choose them because they are all very important. I want to describe several operations within a group. So generally you keep in mind the case of a finite group, but so many of the things that we will discuss are meaningful quite generally for any group. The first operation that I want to describe is called the operation of conjugation. What does this operation mean? It means the following: the conjugation of an element A by an element B leads by definition to another element A prime, let us say, equal to BA B inverse. We say conjugation by B is the operation or the procedure by which A is led to A prime, A is mapped to A prime by this rule. So you have to imagine conjugation by B is something in which B is fixed and A is allowed to vary. So this symbol here runs over all group elements and you get various results from here. All right. You can easily see by the cancellation rules If you take two distinct elements A, what you get by conjugation will also be distinct. B is the same in both cases. So this is conjugation of one element by another element. And then we also say A prime and A, we give this a name, or we say they are conjugate elements. So more generally, given any two elements A and A prime in a group, when shall we say that they are conjugate to each other? If and only if you can find a third element B such that A prime equals B, A, B inverse. So this is the definition. Two elements A and A prime are conjugate to each other if there is a third element B such that this equation holds. So strictly speaking, I should have said A prime is conjugate to A if this equation is true. But if A prime is conjugate to A, is A conjugate to A prime? Obviously. Why? Because you can move the B factors to the left, and if B carries A to A prime, what carries A prime to A? B inverse. So it's a symmetric relationship between A and A prime. To be conjugate to one another is a symmetric relationship. Then you go one step further. You say that each element determines something called an equivalence class or conjugacy class, which I write by this notation, script C of A, and by definition it consists of all those elements of the group A primes which are conjugate to A. Also we can call them equivalent to A. Maybe I should add here equivalent elements. Well, this word equivalent is also used so often, it always has to be understood in the relevant context. So what is the conjugacy class of an element A, or the equivalence class of an element A? It consists of all those elements of the group which are conjugate to A. And can now you tell me a formal way of indicating all the elements which are contained in this script C of A? What may I write here? How do I compute, how do I find out the class of A? What should I do? Yeah, so rub out A prime. Then what can we write? All you have to say is this is a subset of the group where we allow B to vary over the group, but of course you keep A fixed. You are finding out the equivalence class of A. And just one more caution, you omit repetitions. So suppose one element B1, another element B2, both lead to the same result, don't write both, just keep one of them. So the equivalence class of an element in a group is defined in this way. It's also called a conjugacy class. Now this definition is very, very important, and I will mention some of the properties only orally. Some things I will write down. Different elements in general have equivalence or conjugacy classes of different sizes. That is to say, the number of elements in the class of A can vary when you vary A in general. As I said, keep in mind the case of a finite group for many of these things. For example, what are the contents of the equivalence class of the identity element? If I put A equal to E, what will I get on the right hand side? Always I'll get E. And I said don't count repetitions. Shouldn't write class of E equals E comma E comma E. Don't do that. So this is just a one element class. Just an illustration that in general different elements have equivalence classes of different sizes. Now here are the important properties of conjugacy classes, and this I just write and I ask you to verify. Not at all difficult. The class of A is the same as the class of anything equivalent to A, which means an entire equivalence class or conjugacy class can be completely recovered or reconstructed starting with any point in it, with any element in it. Okay, that is first property. So the class of an element is the same as the class of any other element in that collection. Second, so this you please prove for yourselves. Suppose you take one class, class of A, and you take class of B. Can it happen that there are common elements in two equivalence classes? Well, the answer is the following. If B is already equivalent to A, then by property 1, the two classes are the same. Otherwise, this is the symbol for null. They have nothing in common. If B is not already in C of A, its class is completely distinct from the class of A. Two different equivalence classes. Either they totally coincide or they have nothing in common. This is very important. In other words, it is impossible for two classes to partially overlap. I mean, it cannot happen. They have a few elements in common, but each one has additional elements. That can never happen. As a result, you can see.
In quantum information theory now,
Yeah.
everybody talks about monogamy.
Yeah.
Maybe you are monogamy.
Yeah, I suppose so. Right. Yeah. So, one can say that the entire group is the union of disjoint equivalence classes. It is important to appreciate that this is a way of breaking up a group into pieces in the set theoretic sense, if you like, and each piece has nothing in common with another piece. No common elements, no few elements in common, and so on. Let me give you two examples of equivalence classes in two of the groups we have studied, and I think at that point I will stop for today. In the case of the permutation groups, how are classes determined? Well, suppose you take an element P in Sn, a permutation P, you do the following. I am just inventing a notation for the present purpose. I start with the number 1. Then I write the image of 1 under P, then the image of 1 under P, that means the image of 1 under P squared, and so on, until I get something whose image under P is 1. So I stop. This is the first factor. So let us suppose the number of integers in this first factor are m1. Then I choose one of the numbers 1 to n, which is absent here, but choose it any way you like, and then do the same thing. until you cycle back to I2. Let's suppose there are M2 entries here, and so on until you exhaust all the numbers 1 to n. So clearly M1 plus M2 plus M3 etc. must add up to the integer n. It is a fact that the cycle, the equivalence class of P equals all permutations with the same m's. In other words, the cycle structure determines an equivalence class of permutations. It is not difficult, you can quite easily derive this. It involves some amount of algebra. This is a kind of thing which you can only do by yourself, monogamy I suppose. It is very awkward to try to describe it in a class on the board. But when you understand it, then you agree with everybody, yes, we all understand it. So equivalence classes of elements in the permutation group correspond to partitions of n. Every partition of n, writing n as a sum of positive integers, gives one cycle structure. One cycle structure means one family of conjugate elements, equivalent elements. In the case of the rotation group, this is the next example I want to give for the equivalence class idea. The group of, because this is geometrically very appealing, as we will see in great detail later, every proper rotation in 3 dimensions is a rotation about some axis in 3-dimensional space by some angle, a right-handed rotation by some angle. The angle can be anywhere from 0 to 2 pi. Well, there is a reason why one need not go beyond pi, but we will see that later. Equivalence classes of rotations, how are they described? You take a fixed angle of rotation, let us say 15 degrees, but allow the axis of rotation to be anything. So all rotations of a fixed amount, but with various axes, will form one equivalence class. So just as here for the permutation group, a partition of n determines an equivalence class. For the rotation group, the amount of rotation, whatever the axis may be, is what describes or determines an equivalence class. So I will stop at this point. The next topic is the concept of a subgroup. So this is a good place to stop. So now we can all go and watch the match. Any questions? Yeah.
That case A prime equal to BAB results, right? So I can write A prime B equal to BA.
A prime.
For the abelian group, A is the conjugate of itself.
A is always its own conjugate. You can put E there. Every element is self-conjugate. What you are saying is, in an abelian group, there is nothing else. Each element by itself is a conjugacy class.
Classes are
Singletons.
I have one business to transact.
Business, yes.
See, the idea of these lectures is, I always felt, many people have felt that why the Bangalore students alone should have benefit of a course of my course of USA. Now, you should know that I think as it goes on, things will get a little more technical and a little more difficult. So in some, I think eventually people, more and more people may like to have some tutorial. So now I want to ask 2 questions. One is I want to ask question, do people need to have a tutorial? Is there anybody here who feels that a tutorial before next lecture will help? In which case I have to find somebody who will do the tutorial. That will be the second part. But if nobody feels that a tutorial will be necessary, then there is no need to go for the second arrangement.